Welcome, everyone. Today, we're going to pull back the curtain on a single scientific principle that is, no joke, the powerhouse behind two cornerstones of our modern electrical world.
So, what do your phone charger and a massive industrial crane have in common? I know, it sounds like a trick question, right? But the answer is this absolutely beautiful piece of physics that we're going to unpack together. It turns out they both rely on the exact same invisible force to do their jobs. One uses it to quietly change electricity, and the other uses it to create some seriously powerful motion.
Okay, let's dive right in. To really get this, we've got to start with the foundational concept that makes everything else possible. It's a phenomenon that, and I'm not exaggerating, completely changed the world.
And here it is, electromagnetic induction, or Faraday's law. This is the core idea, and it's kind of mind-bending. It says that magnetism can create electricity without anything physically touching. So if you have a magnetic field that's pulsing or moving, it can literally push electrons into motion in a totally separate wire. It's like creating a current out of thin air. It feels like pure magic.
Now look at what's happening right here. The AC supply causes a magnetic field to pulse through this iron core, which links the two coils together. But notice, there are no wires connecting them. None at all. The energy is literally jumping the gap, carried entirely by that changing magnetic field.
So, with that amazing principle in mind, let's meet our first device and see how this idea gets put to work in a way that is just brilliant and yet so simple. This is the device that makes our entire power grid even possible. Okay, so a transformer has two coils of wire wrapped around a core. Power comes in one side, and through that pure magnetic induction we just talked about, it gets transferred to the other side. But here is the critical part, the one thing you have to remember. You need alternating current. A steady DC current, say from a battery, just creates a steady magnetic field, which does, well, nothing. It's the constant change, that pulse from the AC, that's required to make the magic happen on the other side.
And here's the really clever part. By simply changing the number of wire turns on each coil, we can either boost the voltage up or drop it down. It's that simple. If you have more turns on that second coil, it catches more of the magnetic field, and that steps up the voltage. Fewer turns, on the other hand, well, it catches less, stepping the voltage down. This one simple mechanical trick is what lets us send power over huge distances and then use it safely in our homes.
Now, in a perfect world, this whole energy transfer would be flawless, 100% efficient. But as you know, reality is always a little bit messier. So let's take a look at the difference between the idea on paper and the actual hardware. So first, let's just imagine this perfect ideal transformer. It's a thing that only exists in theory, on a blackboard. It has absolutely zero losses of any kind. Every single bit of magnetic energy from that first coil is perfectly and completely captured by the second. Thinking about this perfect version gives us a really clean baseline, so we can see where the real world gets a little complicated.
And boom, this slide just lays it all out, doesn't it? The difference between the clean idea and the messy reality. See those extra symbols on the right that weren't there before? Those represent all the real-world imperfections. The R is for the electrical resistance in the copper wire itself, which just turns into wasted heat. The X stands for other magnetic and electrical losses. These are the things engineers fight against every day to build more efficient machines.
And one of the biggest sources of inefficiency is this thing called leakage flux. You can see some of those magnetic field lines, the dotted ones. They're actually escaping the core and just looping out into the air. They don't link up with the second coil, so the energy they're carrying is just gone, wasted. Okay, so we've seen how to use this invisible force to change voltage. That's pretty cool. But what if we could use the exact same magnetic magic to create actual physical motion? This is where the story gets really exciting.
And that's where the induction motor comes in. You know, it's often called a rotating transformer. And honestly, that is the perfect way to think about it. If a transformer is a static device, the induction motor is its dynamic, moving cousin. The motor's stationary outside part, that's like the primary coil. And the spinning part inside, that's like the secondary coil.
So, what's the trick? How do you make a magnetic field actually move? Well, you use something called a three-phase power supply, which is the standard for industrial electricity. Instead of just one AC current, you get three, all perfectly synced up. And this sets up three overlapping magnetic fields inside the motor's stationary part, called the stator. As you can see, each field is pulsing at a slightly different time, about 120 degrees out of phase with the others. So at any single instant, like a snapshot in time, right now, these three pulsing fields are all combining their forces.
In this exact moment, for example, their combined effect creates one single, powerful magnetic field pointing straight down.
But here's where the real magic happens. As those AC currents naturally cycle through their peaks and valleys, that combined magnetic field smoothly rotates in space. We've just created a revolving magnetic field without a single moving part. The field itself is spinning, and that is the absolute genius of this design.
Okay, so we've got this invisible spinning force. Now we just need something to spin with it. So let's look at the rotor, the part that actually spins, and see how it's designed to chase that rotating field. This is where the motion comes from.
You've basically got two main designs for the rotor. On the left is the squirrel cage rotor, and yeah, it really gets its name because it looks a bit like one of those hamster wheels. It's incredibly simple and tough. On the right, you've got the slip ring type, which is a bit more complex with actual wire windings that let you make external connections.
And this table really breaks down the differences for you. That slip ring motor, with its complexity, gives you a ton of starting torque, perfect for heavy loads like cranes and elevators. But for most jobs, the cheaper, bomb-proof, and super low-maintenance squirrel cage is king. I mean, it's used in over 80% of all industrial applications, powering everything from fans to factory machines.
All right, so let's just take a step back and look at the big picture here. It's just so elegant. We started with a static box that changes voltage and ended up with a powerful motor that creates motion.
The whole point, the crucial thing to take away, is that it all comes from a single law of physics, Faraday's law of induction. In the transformer, we use it to induce a current in a stationary coil. In the motor, we use that same principle to induce a current in a movable rotor, which then gets dragged along by the spinning magnetic field, creating that powerful twisting force we call torque.
And that's why this matters. Understanding this one principle helps demystify so much of the technology that surrounds us every single day, from wireless charging for your phone to the hard drive in your computer. So I want to leave you with a final thought to ponder. Now that you know how this fundamental force of nature works, where else is this invisible force hiding in plain sight? What other innovations do you think we can unlock with it?